Hi everyone, Combinatorics of posets, lecture number 4. Today we have two theorems to prove, announced last time. This is a little bit like extremal combinatorics for partially ordered sets. So we would like to see today that if we don't have a standard example of fixed size, say 100, then the dimension of our poset is sublinear. In n, its size, number of elements. Yeah. Moreover, we will see that dimension can grow, well, and grow kind of polynomially in the size of the poset. So if we forbid s, say again 100, then the dimension can be something like n to the 1 minus some function of 100, where when 100 goes to infinity, this function goes to 0. So in the exponent we are going to 1. And as you can see, this little O of n is not such an old result, and it screams to make it stronger. Yes, and this is the main message I want to leave here, that we should do better. Anyway, both proofs are visually pleasing, and I hope it will be fun, and that we will make it to the end. So let's start. We take the upper bound first. In order to do that, I need to introduce you the notion of the split of a poset. So given a poset, we can make a split of it, and then we'll get a bipartite poset, so height 2 poset. The rule is that when you have an element in your original poset, you produce two comparable elements in the split. Right? From x you get x prime, x double prime, and x prime is less than x double prime. And then when you have a relation in your original poset, so x is less than y, I guess I should write strictly less here. No, okay, maybe it works even with but it's stupid. So when we have a relation in the poset and you look at the corresponding pairs, then the x is less than y, so x prime, so the lower x is below the higher y. Yeah, that's the rule. And you generate a poset. You have an example here on the right. Yes, so you have a very nice 5-element poset. And out of it, you produce a 10-element poset, which is of height 2. And now the thing is, and we'll do it in the exercise session, this is not difficult. The dimension of the split is basically the dimension of the original poset. Okay? So why didn't we do splits all the way through, and why are we not just talking about height 2 poset? Well, something is destroyed dramatically. It's any kind of notion of planarity, structure, stuff. It disappears. Yes, but since in this project here, in this lecture, we don't care. Yeah, we just look at the dimension itself, really, and the standard example number, which will come in the next slide. We are happy with this. So that's the split of a poset. Now we need this little proposition on top of this exercise, which basically says that the standard example numbers stays. Yeah. In order to do that, I need to assume that we are working at least with standard examples of size 3. And this is, if you didn't notice, our theorem is also stated for standard examples of size 3. We know if we are talking about S2-3 posets, I discussed at the last lecture, we know better. This actually coincides with interval orders. We exactly know the maximum dimension there, which grows like log n. So this is really about t greater or equal 3, and in that case, if we don't have ST3 in the original poset, we don't have it in the split. Easy. And the argument is somewhat, there is an argument. So consider the split of a poset. Suppose that you have a standard example of size of order t in the split, and now we're going to argue that we have it in the original poset. Yeah. So what do we have to do? Okay, let me be suggestive here. So in the split of a poset, which here we denote by Q, of our poset P, it's of height 2. So if we have a standard example there, it's pretty clear that the minimal elements of the standard example are at the minimals, and the maximal elements of the standard example are at the maximals. Yes. So so we have the standard example looking something like this. Yeah, it sits here. Now, but elements of the split come from the elements of the original poset. Yes. Actually, here you could have x prime and there was x double prime, and in the original poset you had x. Now, if all the elements, so like perhaps I have S3 here induced on these 6 elements, if all the elements here come from different elements in the poset, we are done. Because these primes, yes, we look at the upset of theirs. Double prime, we look at the downset. If we look at the corresponding elements in the original poset, it's the same structure. So then we have ST, and this is what we wanted to prove. So we need to deal with the silly looking case that within our copy of ST in Q, there are 2 elements that participate in the copy. So say this one and this one, that come from the same element of the original poset. So A prime and A double prime, yes? Please recall that we have a comparability here. So, so these 2 elements, they are in different pairs of the standard example, yeah? Because a pair in the standard example, I mean, is an incomparable pair, the vertical one, yes? So these 2 elements are in different vertical pairs of a standard example, yes? So let's envision the standard example itself. Yeah, so I have A prime here, yeah, and then there is some guy in here. I have A double prime here, and there is a guy here. Now t greater or equal to 3, so there is some other pair that is not hit by A prime nor A double prime. Let's look at that pair. So it's an incomparable pair. So these 2 elements come from different elements of my poset. So that's what I say when this is B prime coming from B, and this is C double prime coming from C. Now this should collapse now, right? Yes. What do we know? B prime is less than A double prime, because it's a standard example, yes? B prime is less than A double prime. A prime is less than C double prime, because it's a standard example. But this relation in Q means B prime less than A double prime means that B is less than A in the poset. A prime less than C double prime in the split means that A is less than C in the poset. So B is less than C in the poset, which means that B prime should be less than C double prime in the split. Doesn't make sense. Yes, so it just doesn't happen. And we have the proposition proved. So, so this is like a obvious first step we do in the proof of the theorem. Yeah, we go down to the split, and the dimension is basically the same, while the standard example number didn't change. I want to do one lemma before we enter the main proof, to not get distracted with some auxiliary stuff over there. So what this is about existence of some binary table matrix, let's call it, yeah, that kind of distinguishes well its columns. So what is it about specifically? So we are going to have Q and T. So Q is the number of columns of our matrix, and R will be the number of rows. We claim that if the number of rows is at least this, it will do. Yes. So you have q columns. Yeah. And now the number of rows is logarithmic in q. I would like to see t as a constant here. Yeah. So my vision is that the number of rows is not so large. Yes. It's logarithmic in q times some function of t. Yes. Okay. So I will claim that something good happen. So this matrix I want to take random. So I flip a coin in every entry. It's 1 or 0, 1/2 each. Yes. And then I claim that something good happens. That's the probability of certain event is positive. What is the event? So the thing is that whatever t columns, here comes t, whatever t columns you highlight, and one of these t you really highlight, then I can find a row that does well. So what does this row will do? I will have zeros in the highlighted columns, except the really highlighted column where I have 1. I don't care about other entries in this row. Yes, so whatever you choose, whatever columns you choose this way, I will find a row that makes me happy. And if I take my matrix, yeah, for given q and t, if I take number of rows at least that, and I flip all these coins, I have a chance to succeed. So it exists. Okay? So this is a rather standard accounting proof phrased here in terms of these probabilities. Let's go over that quickly. So is the statement clear?
More related somehow to color coding. It looks very similar. Okay.
Yeah, open-ended. Yes, yes, yes. I don't know much, to be honest, about color coding, but okay. So what is going to happen? So instead of looking at this one big event, I elect here to discuss small events. So you give me your choice. Your choice of columns is S, so T columns, and one of them really highlighted. L is the index of the really highlighted column. Now the ESL event is the event that I have a row for this choice. And now the probability that this event doesn't happen is really easy to compute, because a single row does the job with probability doesn't do the job with probability if what do I want? Okay, I really want in these T columns, I want specific T values, T bits, yes? So T columns are highlighted, one is really highlighted, yeah, and then a single row does the job if I have 0, 0, 1, 0, 0. So I have T entries that I really want to see. So the chance that I see these T entries is 2 to the 1 over 2 to the T. The chance that I don't see it is the complement. And now if the event doesn't happen, then it doesn't happen in all of the rows which are chosen independently. So that's why we have a power R, yeah, number of rows. Okay. Now the probability that good thing happen in total is the probability that for every choice of yours, a good thing happens. And this is the same as the probability 1 minus that the union of bad things happen. And this looks like a union bound. And now we have to focus. So this is the sum, of the choices of S. Yeah, you choose T columns out of Q. So this is Q, choose T. Then you choose what to highlight. This is T. And then it's the probability, which is the same for every choice. Yeah, it's this pre-computed before. Yes. So we have this. Now this bracket, we should apply the usual estimate here. Yes. There is a negative sign in front of it, so it applies here with the right direction of inequality. Something also happened here. This binomial coefficient disappeared. Instead of it, we put Q to the T. So it's an upper bound on the binomial coefficient, but it comes with a negative sign, so everything works well. We need to elect somewhere to put the strict inequality. I think for many reasons this is strict, so let's put it here. Then if we have this, what's going to happen? Okay, we change the base. Instead of Q, we put E. So we have T, L, and Q. And then it's the time to plug R. Yes, it works if R is large enough. Yeah, and R was chosen to be T times 2 to the T, L, and Q. So if you plug it, then you see you have T, L, and Q here. 2 to the minus T to the T. It cancels out. T, L, and Q. So this actually disappears. Right? No, this actually, in the exponent you have 0, so it's 1 minus 1, 0. Any questions? Something? Would like to see something cleaner in this line? So at the end, the message is that if we want to have Q columns and we want to be ready for all these choices, it's enough to take this number R of rows. Q columns, and we allow the adversary to give us kind of t-tuples as choices. Yes? Okay. So that was the proof. Now we go to the theorem, to the proof of the theorem. Yes, so dimension is sublinear. Hooray! So here is the poset, n elements. This is what we expect, easy stuff. It's ST3, no standard example of order T. We take the split of the poset. And as we discussed, it's a n element poset. It's height 2. And the dimension is pretty close. I need an upper bound on the dim p. And as we also have seen, it doesn't have a ST as well. Okay. So we are going to concentrate now on bounding dim q itself, and we're going to show that it's little o of n. So when we look at q, recall it's height 2. We have elements at the bottom A and at the top B. And for the rest of the argument, I would like to fix some linear order on A, of your liking. Now, when we have T elements chosen from A, yeah, and I would like to they have indices A1 to AT, and I would like these indices to respect the linear order behind. So it's really t-tuple. I would say that an element B is a mate, actually an I-mate for this tuple, if this happens. So this element B relates quite well to the tuple. It's above everything but the ith element. And then it's an I-mate. It's a kind of threat. Yeah? It's a kind of threat for this tuple. Yeah? You have T elements at the bottom. An element is a mate, an I-mate, where I is an index from 1 to T. Yeah? If this element is above everything but the ith element of the tuple. Now, since our Q is ST3, we know something. Marek, it's okay?
Is it like opposite of the thing at the bottom?
Yes, it's exactly the opposite to what it's written. Yes, sorry.
So what will you
It's-
opposite or the picture?
The picture is good. The picture is good. Apologies. And what I say is also good. The-
That's kind of fun.
yeah, sorry. Q is ST3, and this exactly means that for a fixed tuple S, you cannot have all the mates from 1 to T, because these mates together with your tuple would construct ST. That's the idea of a mate. Okay? So this gives us a possibility to color the T tuples. Yes? So now fix a coloring of the T subsets of A, yeah, with T colors, such that you want to have that when you have a tuple S, it doesn't have a phi of S mate. Phi is the coloring we do, yeah. So S, there exists I such that S has no I mate. So I is a potential color. You choose. And that's how you color, okay? Is it clear? Good. So we have a very nice coloring of the T tuples. And now please consider with me a monochromatic subset of A. So it should imagine that we have it. Yeah, we have this coloring. If A is large enough, we can Ramsey out some monochromatic subset, but let's skip that part for a moment. Let's consider a monochromatic subset C. So C of A. What do I mean monochromatic? Well, say that C has Q elements, yes? And then what I want is that every T subset of C has the same color under my coloring, yeah? So the same color will be called L. L is the color, it's a value between 1 and T. Okay? Well, maybe some visualization. Yeah, so we have elements of A, we have elements of B. These elements were subject of our coloring, A, yeah? And now we elect some elements of A, yeah? This is C, subset of A, such that every T subset of C has the same color, and the color is L. Okay?
So are we trying to extend the coloring that we gave earlier to larger?
No, the coloring is just on the T subsets, and T is fixed. T is the size of a standard example that you don't see. We just the coloring is just of the T subsets of A, yeah, and for now you just consider a subset of A, C, such that every T subset inside of it has the same color. That's it. What are we going to do with it is we're going to say, yeah, because these elements behave somewhat uniformly to what we understand, or to any, this is the only leverage that we have. And they kind of behave in the same kind of way, and we want to exploit it. So we're going to say that we can reverse them. What does it mean to reverse? We reverse incomparable pairs. So what kind of incomparable pairs we are going to reverse? Well, those from C cross B. Yeah, all the pairs such that the first coordinate is yellow and the second coordinate is anything here. We're going to say, yes, we can reverse them efficiently. So we claim that they can be reversed with Q prime linear extensions, where Q prime is given here. It's basically a constant depending on T times logarithm of Q. Why is it good? Q is the size of C. And we are reversing all these incomparable pairs with a number of linear extensions being logarithmic in Q. This is a good trade-off. So if we are able to repeat it, yeah? So we have a coloring. We take a monochromatic subset. It's of size q. We use logarithmic in q number of linear extensions. Flip them, reverse them all. Forget about them. Consider another monochromatic subset. Yeah. Take out another q element, say. Yeah. Logarithmic in q linear extensions. This is quite good. Yeah. So if we are able to repeat it, this should be a realizer. This should give a realizer that has a decent size. We should be able to save something. Yeah, the saving is when you compare the size of C, which is q, with the number of linear extensions here, which is logarithmic in q. Okay, and the proof of this claim is the main technical contribution here. Samuel.
Why do those chromatic subsets C exist?
No reason now. Just consider with me such a monochromatic subset. Well, I mean it exists. Come on. Well, you have a T coloring of a T subsets of a large set. Yeah. If A is large enough, and we are doing asymptotics in N, then you will find something. Yeah. This guaranteed size of a monochromatic subset grows with N. It's a rather slow growing function, but it grows, and that's our leverage. Yeah. But I will really explicitly cover this part when I'm done with this claim. Just take with me this monochromatic subset and let's kill it, and then we will see. I was really careful at the end of this argument, also on slides. So claim. I want to prove this claim with you, and it's repeated here at the top. And how do we do it? So our guideline will be this matrix that is given by this lemma before. So we apply the lemma. I made it so Q and T agrees with in the statement of the lemma. So basically, the matrix that we get out of it has Q rows, yeah, and the number, Q columns, excuse me. And the number of rows was T times 2 to the T times ln cube. Yeah, that was guaranteed by the lemma. So we take it, and note that the target Q prime is twice larger than the number of rows that we have. Yeah. So. Our goal here basically is, the construction goes that for each row of the matrix, we will construct 2 linear extensions of the poset. And then we will have a set of linear extensions which is exactly of size Q prime, the target size. And then we're going to argue that this set is good, realizes these incomparable pairs in C cross B. So, for each row of the matrix, construct 2 linear extensions of Q. So let's have a look at the row. Yeah. So I look at the row X. This row. It has Q entries because the matrix has Q columns. So in order to construct a linear extension of the poset Q, so Q is on A and B, we first devise a permutation, actually 2 permutations of A itself. Yeah, A is an antichain, so in a linear extension we can permute it however we like, and here is how we like. So we, for the sigma left, for this permutation sigma left, what do we do? So this row has some zeros, yes, and some ones, yes. But okay, the missing thing that I was looking at is C. So I have C fixed here. C is this set of Wait a second, I lost my... No, it's okay, it's okay. So the matrix has Q columns. This actually coincides with the size of C, yes? But in the poset Q, yeah, we have elements in A that are in C, not in C, and some are in C, the yellow ones I highlighted here. So when I construct now sigma left, yeah, which is here on the slide, what do I do first? Is I take all elements in A that are not in C, and I will put them somewhat in the bottom of the linear extension. They are not of my interest, yeah? So A minus C, which is here on the slide, this is put first, at the bottom of the linear extension, target linear extension. Then I take elements of C, but those that corresponding, so each column of the matrix corresponds to an element of C, yeah? They are listed here, and they are listed here in the columns. And now when I read my row, I have some zeros and some ones, yes? I put all elements of C that the corresponding entry in my row is 0. I put them next. Not of my interest. Yeah. And then eventually I put those elements of C that the corresponding bit is on. And here I care about the ordering for the first time. And I do it, this is sigma left, so I do it from right to left. So I read it from here to here. Yeah? Those yellows that corresponding bits are on in my row, yeah, are listed from right to left at the very front of what I'm doing there. The sigma right is exactly the same. The exception is at the end, where I list it from left to right. And now I complete the definition of the two linear extensions. So I just listed you all the elements of A in sigma left. Now in order to make it in a linear extension, I have to tell you where are the B's. This is very simple. Push them as low as you can. Yeah, the B, which is a maximal element, you try to push it, yeah, and it will be stopped by some element A, which is below it, because you cannot go below, because you must respect the poset. That's the definition of L left and L right. I can take some questions now. The goal is here that we produced a set of linear extensions, and we claim that this realizes what we want to. So the goal is that for every incomparable pair, CB, that is in C cross B, yeah, so a pair that element C is here and element B is here, and they are incomparable, I have a linear extension in my set that puts B before C, that puts this element above, below this element below. Yeah? For every BC, for example, for this one here, given that they are incomparable. Okay, so we need to prove it. So, fix CB in CB incomparable, yeah? Now this element C is in C, so it has an index, yes? C has Q elements from C1 to CQ, yeah? And this element C, say, is the ith element, yes? Okay? So there is a column that corresponds to it in my matrix. Now, now I need to trace how this B behaves on my linear extensions. And I need to understand what stops my B. And these M left set and M right set will be just about that. So M left, say, is the set Cm of all C's such that Cm is less than B in Q and M is less than Y. Yeah, so what do we have here? What do we have here? We have an element C, Ci, that we are looking at. And we are collecting other elements from C, so other yellow elements, yeah? But those that are left, yeah? So these are the potential elements. And those that are comparable with B, yeah? So maybe I take this one, maybe I take this one. Maybe this and this is an M left, okay? M right, pretty much the same. Those in C, such that, again, we have a comparability in the poset between Cm and B, but this time M is greater than I. So those on the right, yeah? This one would be an M right. Now, the critical observation here is that one of these sets is small. Yes? So either M left is less, we can even put less than L minus 1, or M right is less than T minus L. Because otherwise you have L minus 1 elements here that are yellow, and T minus L elements here that are yellow, and they together with your element form a T-tuple, and this T-tuple has an L mate, because Ci is elf in the T-tuple that I just described. It doesn't happen. So this holds.
What was L and I?
So L is this color that is used on all the T-tuples in C. I is the index of C that we're talking about here, that we want to reverse C. We want to reverse CB. So we constructed these two sets looking at our CI. This is just the ith yellow, yeah, just that. And there are many yellows here that I didn't list it, yeah? And the thing is that this B cannot send comparabilities to L minus 1 here and T minus L here, because you would see a T-tuple with an L mate doesn't happen. T-tuple with all elements yellow, so all elements in C. Okay, so if we have that, we're happy. So let's simplify our life. This is less than T, and this is less than T, okay? I give up something. Now there are two cases, yeah? One of this holds. And what do we do? So in the case that, say, this holds, it's time to say to which row we are looking at and to which linear extension we want to look at in order to see that B gets below C. So, and we need to use the property of our binary matrix. So we have less than T yellow elements here, we can, yeah, so these elements, let's make them orange now for a moment. So we have these orange elements, yeah, less than T. Let's take Ci with it, yes, and let's complete it. So this is still less or equal T. If it's not T, complete it with some yellow, whatever. Make a T tuple of elements of C. Now, this T tuple with the index of Ci in this T tuple highlighted has a row in the binary matrix that I hope is here. Yes. In this row, so there are orange columns, and one of them is red, the one corresponding to Ci. This is what I want. And my row is good if I have 0 here, 1 here, and 0 here. I don't care about the other entries. Okay. And now we have this row X. Now we should understand if we are looking at the L left generated from X or L right. What's your guess? Left? Is it just 50-50 or because I want to follow you? I don't know.
Ah, okay. Because we took M left, so.
Yes, but you kind of assume that there is some logic in what I'm doing. Yes, so let's look at L left generated from this row. The claim is that B gets below C in that linear extension. Why is it so? So let's recall what's the definition of L left. Well, maybe I can use my slide. Yeah, so that was the definition of sigma left, so the elements of A. Elements of B were pushed as low as possible. So this is a critical thing. First question, where is our element C, Ci? It's a little bit misleading because these Ci's are, where is the Ci that we talk about? It's in this set here, yeah, because it's an element of C, so it's not here, and it's highlighted in my row, so it's here, right? Yes, and now it's important that we sort this from right to left, yeah, so we kind of read these elements from here to here. Be good? Maybe, we'll see. Okay, from right to left. So now we are taking B. We are in the case that M left is small, right? We are taking B and we want to push it over these elements. So why this element is not higher? No, we should sort it the other way. No? We should sort it the other way. I should have these elements at the top because I know that I can avoid these because they have zeros. I think. Yes. So let's look. Let's look at L right, just because still the Ci stays in this set, of course. But now I want this set to be listed from left to right. And now I want to say, okay, I push my B, and I want to get below C. Yes? So what can stop me? Only those elements that are highlighted as 1 and are below B. So these are the elements. The elements below B are in M left. And exactly these elements were in my tuple that corresponds to this row. And these elements have 0 in my row. So they are not in this set. They are here. So they are not going to stop me. Some other yellow maybe are here, but I don't have relation to them. This means that C is exposed and B can pass C.
Well,
Excuse me?
The oranges to the right.
What about what?
Because like there are orange guys to the right of CI.
They are to the right
They
of
might
CI.
have one, and they will be above CI, so you won't be able to push E below CI.
But wait, so in L right,
Am I mistaken?
in L right, I am listing it from left to right. Ah, okay, you are actually right. I missed the. Okay, this is because of looking at it horizontally instead of vertically. So yes, so there is A minus C. Apologies. There is A minus C. There is this C that is off in my row, and there is this C that is on. Yes, and now if we are not confused again, the thing is that we want to list it here from right to left. Correct? Which is actually L left. Okay. And the reason is that I want to have at the top, at the right here, I want to have left elements. Thank you. I want to have left, because B is sitting on the top here and is trying to get here. And my argument was that B can pass all potential threads here and get to C. Okay? I think it clicks now. So that's actually a proof. That's a proof of this claim here above, that these incomparable pairs can be reversed. And we should be happy how efficiently we did it, in a sense of the number of linear extensions, and maybe not the length of the presentation here. Let's go back to the main proof, because we're wrapping up somewhat. So we should discuss kind of inverse Ramsey here. Yes. So not the Ramsey that I'm used to, at least. So one index here should be for the number of colors we use. One index should be for the size of the subset that we color, subset of the universe. And the last one is the size of the universe now. And I want to produce out of it the guaranteed size of the monochromatic subset. So all I know is that for 2 to n I have 1/2 log n. Yes? Now, we're not going to color, we are t-coloring t-subsets, yes? And now, let me get back to first. I want to fix some function g of n to make it clean. I don't need much of this function. It is almost anything. You can think of it of square root of n. Absolutely perfect, okay? What is important for the argument, I'm saying that to not confuse you with the magic properties of square root of n, is that it should grow, it should be monotone. Actually, I'm not sure about it when I was typing my slides. And it should be little o of n. It should be sublinear, okay? So take this gn, your favorite gn, and now we go back to the Ramsey. We are t-coloring, yes, we are t-coloring our t-subsets of our universe. And now the universe at the beginning is of size n, that's n elements in A. I want to be ready for a universe of size gn. So gn like square root of n, for example. And then out of this, I have some guaranteed size of a monochromatic subset. And from the properties, from the obvious properties of Ramsey setup and Gn, we know that Cn grows to infinity when n grows to infinity. Yeah? The larger the universe is, the larger the guaranteed subset is. Yes? And it's monotone, which maybe is even not important in my wording. Here's the final thing. What are we doing? Dimension of Q. We are constructing a realizer, and its size will bound dimension of Q. How do we do it? Well, as long as our universe of A is at least of size Gn, of not done A, we find this guaranteed monochromatic subset of size Cn. And we use this number of linear extensions to reverse all incomparable pairs between the subsets, so the C, it used to be C cross all the B. Yeah? So this is the number we use in one step, and the number of possible steps is upper bounded by the size of the universe divided by the number of things you take out in a single step, lower bound on this. So the lower bound is Cn, yeah? It can be exactly Cn actually, because we can just take this subset. So at most this number of steps, I produce this number of linear extensions, and then I get to the moment where my universe, the remaining A's, is less than Gn, less than square root of n. And there I want to get brutal. And I want to say, okay, let's take one or two linear extensions. Let's take one linear extension for each. Yeah? Take your A that remains, put it at the top of all the A's, and push all the B's that are incomparable below it. Done. All the things, yeah. In the bipartite poset, yeah, you can do this. One linear extension to kill this kind of. So we have at most G of n elements remaining in A, and for each I use one linear extension. Super inefficient. But I claim that we did well before. So I just want to complete it now and go home. Okay, so this is what we've done, and this should be essentially realizer. We reverse all the incomparable pairs between A and B. There are some silly ones now, perhaps. So those in A, those in B, but this can be done with two linear extensions. So that's the +2 at the end, and that's legit. It's a realizer of Q. So now we just have to understand its size, and I was preparing to be ready for this here. Please note that 2t, 2 to the t, yeah, this +2, this is like some constant depending only on t. Then I have n. So constant is not a problem. N is a problem. This n is a problem, yes? And then what is left is log of Cn over Cn, this Cn, yeah? And then there's plus Gn. Now, our choice was that Gn doesn't grow linear. Square root is not linear, yes? So this is not a problem. But our choice also was that Gn was fast enough, so Cn goes to infinity. And since Cn goes to infinity, log of Cn over Cn must go to 0. And because of that, this one kills this n to be little o of n. And that completes the proof. So do we have questions?
So, if you have any class of posets where you have those Ramsey numbers better, like a polynomial or something like that, you immediately get strongly sublinear result.
Yes. I didn't even look at this angle.
Okay.
We would have to kind of understand what this Ramsey is there, yeah? It's crazy coloring.
I'm just asking because this construction that you, this Ramsey construction that you did is in model theory the same as taking an indiscernible sequence. And there are classes where you can get better bounds, Ramsey bounds.
I see.
So are there known results of this kind, that for some classes of posets you get better extremal functions?
Well, I mean, look, in the planar setup, for example, we claim to have a constant, right? Something comes to your mind, Tom?
No, in fact, it won't work. Just remember what models that you have for posets in general, and if you talk about, for example, labeled ones essentially look like any chain of size n over 4 and any chain of size n over 2 and any chain of size n over 4 with the comparabilities put in at random between the middle, it's essentially this bipart.
In all posets, yes, you will probably not be able to get better than rounded bounds.
Yeah.
So he's suggesting that maybe instead of taking all the class of all posets, there is some interesting class of posets that has a better Ramsey number here corresponding. That's the thing. Yeah. But at least there's nothing.
Once you start taking splits, though, you kind of give up your interest in.
That's actually a good point. Yes, we kind of that was very. I even presented in such a way that was I really give up everything here. If you think about structure or something, just making this split. Yes. So that's a step. Yeah.
Split is not okay. We can take it offline.
Sure. Thanks. Yes. There is one more proof to be done. Let's. We will see how much we will do. Maybe I skip proof of one of the claims just to give you a picture and not get back to it at the last lecture tomorrow. So that I want to prepare a lower bound here with you. Yeah. So the claim is that if you don't have, for example, S3, standard example of size 3, then dimension can grow like n to the 1/6 over log n. So yes, so it grows substantially. And here is a setup for the argument. So this time we're going to take a random poset. It will be height 2. We start with n elements at the bottom and n elements at the top. Since we're going to take a subposet of it, eventually the subposet will have exactly n elements, yes? But now we have 2 n elements. And on each possible edge here, there are n squared. We flip a coin independently. So with probability p, we put a comparability. With probability 1 minus p, that we sometimes call q, it's incomparable. Now this p is carefully crafted. And I don't want to tell you that now, not because it's so horrible, but I don't want to distract you. I just tell you that the p will be something like 1 over n to the alpha. Alpha will be some healthy constant between 0 and 1. So definitely p will be less than 1/2. Okay? This alpha just depends on t. Not so dirty function over there. But that's the setup at the moment. And now there are 3 claims. And a very short argument to wrap them up. So given that p is less than 1/2, and actually this claim would work also on a much milder assumption on q, we have almost surely the following thing. If you, okay, let me clean the boards first. If you look the A's and the B's and you look at the incomparability graph, so the complement of the comparability graph, yes, then almost surely you will find a perfect matching between A and B. Almost surely you find incomparable pairs like this. Okay? That's claim number 1. Claim number 2. Almost surely you're not going to find 2 large subsets, one of A. So this is claim number 1. Claim number 2. Almost surely you're not going to find A prime and B prime such that they are of decent size. So here it's 3 log n over p. Please recall that p is something of the kind 1 over n alpha. So 3 log n over p means n to the alpha times 3 log n. So you're not going to find one subset of A of this size, one subset of B of this size, such that there is no comparability between them. Yeah, such that this is completely independent, yeah? No comparability set here. You're not going to find it. So please note that these two claims kind of balance out what you see. We choose P in such a way that on one hand we want to see some incomparabilities. Yeah, please note that the complete bipartite graph you want to see, in general, you want to see some incomparabilities and some comparabilities because the two extremes have low dimension. And this is like our take here. How do we want, what do we want to catch? So on one hand, you want to see these incomparabilities, so the matching. Yeah, on the other hand, given two large subsets, you do want to see some comparability there. Yes? Okay, that's the two claims. And the third claim is a nice statement. It's just that the expected number of STs that you see in such a random poset is bounded by some fraction of it. Okay? So what do we do?
N over 6 goes very quick to 1.
N over 6 goes very quick to 1.
Okay, no, it's fine.
Ah, you thought it's a probability. Yeah,
That's me, I think.
it's okay. Because I want to be sure that I make the final sentence here in this, let me first skip the proofs of two claims. I am ready to show you that, but this will be pretty tight. So let's do claim number 3, because expectation is much nicer than probabilities, and let's make a final argument, and then we will see where we're at. Okay. So proof of the claim 3. So x is this random variable, sorry. The number of copies of ST in Q, we call it Q, right? Now I want to take a sum of indicators here. Yeah, so for every possible position of a standard example, I want to have an indicator if it is there or not. So what is a position? Well, it's a subset A prime of A, a T subset, yeah. I'm talking about ST, so we have T elements at the bottom. It's a subset of B prime, yes. So this is an indicator at the specific subset. Well, and then I need some permutation. Let's call it pi. Yeah, and then so if you have A and you fix some A prime, and you have B and you fix some B prime, yeah, both of size T, and you still need to tell me what are the vertical pairs. Yeah. So if this is say A1, where is B1? Yeah, it could be here, for example. Yeah. Yeah. So that's the choices that we can make, and then so once we fix the subset and the bijection, we can tell if this is a standard example in the poset or not. So we are going over all A primes subset A prime size T. We're going over all B primes subset B prime size T. And we take all permutations of T, yeah, to fix the bijection. And then yes, so so the expected number by the linearity is the sum of the expected xa prime b prime pi. And now so this is just the probability that at this position, we have the standard example. So how do we bound it? So the choices of A prime, this is n, choose t, right? That's the choices of A prime. The choices of B prime, that's n, choose t. The bijection, this should be t factorial. Then we need to see certain comparabilities and certain incomparabilities. There are exactly t incomparabilities. So incomparability is 1 minus p to the t, and the rest are comparabilities, and this is t times t minus 1, right? Comparabilities. Okay, so that's it. Now we just have to understand what did we write. So these two binomial coefficients, this is bounded by n to the 2t. Yes, one of the factorials can cancel out. From the other factorial, I want to save 6. Yes, because so 2 times 3. This will be handy at the end. So let's keep the 6 in the play. And then what? And then both numbers are below 1, so we could forget about it. We can forget about this one. Let's take this one. And this is the moment where we need to wake up and say what is actually p. Yeah. So p is actually n to the n over 1 over n alpha, and alpha is chosen to be 2t minus 1 over t times t minus 1. That's the power. Okay? And it's chosen in such a way that when you plug it here, n to the 2t over 6, 1 over 6 times n to the 2t times, now what do we have? So it's n to the minus, and then I put this 2t minus 1 over t minus 1, and then I have this power still. So this is times t minus 1. So you see, this was exactly chosen to cancel out here. So we have n to the 2t times n to the minus 2t minus 1. So, yeah. Okay. Very good. So that's claim 3 proven. Now, given the first two claims, the proofs are of this length. Okay, nothing hidden there really. But let me show you the final line of the argument when we have the three statements. Okay. So at this point we have to say, okay, we have our random experiment and we take the outcome, which happens with a positive probability, yes? So what is the outcome? So this is, we have to switch the probabilities here. So the probability that the number of STs is greater than n over 4 is by Markov at most the expectation over n over 4. And the expectation is bounded from above by n over 6. So this is at most 2/3. Okay. So with probability 1/3, we have a number of linear copies of ST. At most n over 4. Okay? With probability 1/3. Now, I want to have this perfect matching. So with very small epsilon, I don't have it, and I have enough space in my probability. And here, I want to have this property, which doesn't happen with a very small probability if n is large enough. And I have a volume 1/3 here, so I can have the two claims. Yeah. So I take the poset that exists, that has this property, and the number of copies of ST is at most n/4. And this poset is a result of our experiment. So still, let's call it Q, and it's n elements here, and n elements here is height 2. Okay. So what do we claim? We claim. Okay, we're not done yet because we have STs and we want to have ST3. So now it's the moment that we are removing these copies, right? So we, for each copy of ST, choose your element that you like, yeah, and remove it from the poset. Since we want to keep the matching here, we are also removing the mate of it in that matching, yeah. So this way, we remove at most n/4 elements from the top and their mates n/4 elements, yeah? So this is like gone, yes? And then we end up with a poset here, say, that we still have this matching. And the number of elements here is 3/4 of n, 3/4 of n. We can make it n/2 now to give it up. And that's our poset Q prime on n elements. It's ST3. It's ST3. So now it's only about the dimension. And the thing for dimension is as follows. You have these incomparable pairs here. And the claim is that they are hard to reverse. You cannot do them like in packages. So the claim is, and this will be because of this, of claim 2. So what is claimed here is that if L is a linear extension of Q prime, then L reverses less than 2 times this number over there, which is 3 log n over p, vertical incomparable pairs. By vertical, I mean those from the matching. Okay? You cannot reverse more. Why is it so? Well, why is it 2? Shouldn't it be 2, maybe? So if there is this linear extension, now let's put some colors. So say these elements are red, and these elements are yellow. And if there is a linear extension that reverses a lot of red, yellow, vertical, then take the first 3 log n p yellow. So you have yellows here, you have reds, yeah? Take the first log n p yellow, yeah? And there are still 3 log n over p red after them, because we are reversing all of them, yes? So so this happens in the linear extension. So these are elements of A, these are elements of B, and they are put before in the linear extension, which means that there is no possible comparability between them. This violates the statement of claim 2. So you cannot reverse them in large packages, which will immediately give you bound on dimension. Yeah, because in order to make a realizer, you have to reverse them all. So, so the final line is that the dimension of Q prime is greater or equal than the number of vertical pairs that we have, that is n over 2, okay, divided by the number of pairs that we can do in one linear extension, and that is this 2, 3 log n over p. Okay, so now we have to do the math, which is always dangerous. N times p over the 2's don't cancel out, right? That's 4 times 3, that's 12. Wow. Every time a different constant. N times p, where is log n? It's at the bottom. That's good. Okay, and then p is n1 over n to the alpha. So this is n1 minus 2t minus 1 over t minus 1 over 12 log n. That's what was claimed. I wasn't here.
Could you repeat why we can't reverse many vertical pairs?
Sure. Imagine that there is a linear extension that reverses a lot. So this number. And then what do you have there? If you have a single vertical pair that is reversed, how does it look like? So it's first you have yellow, and then you have red, yes? In the linear extension, yes? So doesn't it mean that if you take a group of first half of yellows, you have still a half of reds ahead?
I don't understand.
So that's why there is 2 in this
Yeah, so thanks. It will be a little bit clearer if I tell you this was the first half of yellows. So there is a second half of yellows. And reds of these yellows must be right of them. Very good that you asked, because that line maybe is helpful. Yes. It's okay?
Okay, so now that I have that, how do I conclude using
Now it's easy, because these are the elements of B and these are elements of A, which means that there is no comparability in the poset, and that violates the claim. Yeah. So I elect not to prove you the two claims. They are short. We could do one of them actually still in the 8 minutes of the lecture, but it's not insightful. It's just you know, writing down what is the probability and then estimating it. It's just that, yeah. And the value of p doesn't really operate there. As I told you, the value of p was really here. That was where you need the definition of it. And here you just need mild assumptions like it's, you know, less than half or something like that in order to work. That it works. Okay. So that's the two extremal type, I like to say, results on poset dimension that we have. And again, we are really missing some upper bound here. So I hope one day we make it. Maybe some of us, some of you. course, it's a wild guess that it could be improved, but this is what happens in graphs, yes. And so far, our gut feeling was good. Just that was a good source of intuition over there. Yeah. So tomorrow, so that's supposed to be a difficult lecture, and so if you are still sitting here, it means that maybe tomorrow it will be easier. So I'm not going to do some big proof tomorrow. I will switch and show you one variant of poset dimension. I'm honestly not really into variants. There are some, and Tom did quite a good job. And there's a local dimension and a nice statements over there. There's fractional dimension that I don't know much about even, but I know one beautiful statement about it. My favorite variant, and some of us even say that this is more natural than dimension itself, is the Boolean dimension. And I want to tell you about it mostly, well, for one reason is that, okay, there is this natural field, yes, and second, that there is a really cool open problem there, which drives research, and yeah, so it'll be good that you know the setup, and maybe one day with your understanding of, for example, planar graphs, because this will be again about planar setup, planar graphs, planar posets. So this will be tomorrow. Meantime, we have a exercise session. God knows what will happen. See you there.